Okay, this is Ana Douglas solving a couple of multi-choice questions for polarization module. So the first one is say that we have two optical polarizers that they are localized in tandem. So we're gonna have here our optical axis here. This is gonna be our optical axis to place the two polarizers. So here I have one polarizer, and here I have my second polarizer, and I know that the angle between them is 45 degrees between their transmission axis. So let's say that I'm just making up this one, but let's say that this is like the transmission axis. So the first one is vertical, so the second one is gonna be sorry, I meant to change the color. The second one is gonna be 45 degrees, right? So we have here some output intensity I1, and after the second polarizer we're gonna have I2 that we can apply Malus law to say that that's gonna be I1, the input in intensity cosine square of the angle between both of them. So here we can do like the cosine is gonna be a square root of 2 over 2. So here that's gonna be half of the intensity of the input. Now, and that's what we know. We know the relationship between the incident on the second polarizer. So they ask us to know the ratio of the incident intensity with respect to the first polarizer. So they're asking us to know based on this. So we need to know what is gonna be the output intensity of the first polarizer with respect to the incident. And a priori, we don't know, we don't have enough information. However, let's say that the input light is natural light. If the problem was saying that the input light is natural light, that means that we're gonna have randomly polarization, but we can always express it as two orthogonal polarization state. Then the input light is gonna be related with the output of the first polarizer as half of it. And now if we are plugging here, so if that one is gonna go now here, then we know that it's gonna be 1 over 2, and then we have here 1 over 2 our input intensity, so the output so the relationship between the output intensity after the second polarizer is gonna be 4 times the incident one, and that means that that's gonna be our dissolution, but only if the input light is natural light. All right, so the next problem is that the data that we have a beam of light characterized with a Jones vector, and we need to estimate which one of the following vectors, Jones vectors, do not represent our orthogonal polarization state. So we know that we have our orthogonal polarization state if the product of the vector Jones with the conjugated of the second one, the scalar product, that needs to be equal to 0, right? So for the first one, we have that E2 is 1 over a square root of 13, 2 minus 3. So if we do the cross product, if we do A1 scalar product, no cross, sorry, scalar product conjugated, we're gonna have 1 over the square root of 13, and the 1 over the square root of 13, that's gonna be the same, and then we have 2 multiplied by 3 minus 3 multiplied by 2, and that's gonna be 0, so it's orthogonal. We are checking it. For the B case, we have here the same normalization, but we have minus 4 over 6. So if we do our scalar product, where we need to conjugate the second vector Jones vector, but it's already real, so we don't need to do it. We're gonna have minus 4 multiplied by 3 plus 2 multiplied by 6. That's already 12, minus 12 plus 12 is still 0, so it's also orthogonal. The last one is the one where we have 2 over 3, both are positive. So when we do the product, the scalar product, then we're gonna have the same normalization, but we have 2 multiplied by 3 plus 2 multiplied by 3, so we have 6 plus 6 is 12 over 13. So that's different than 0. So this is the Jones vector that does not represent our orthogonal polarization state. The next problem is the 14, where they are telling us that we have natural light. Oops. So we have here natural light. So we have here natural light, right? And it's going into a horizontal linear polarizer. So we're gonna have here only horizontal linear polarized light. So if we start here with 50%, we have here 50%. Then that goes to a half-wave plane when it's oriented at 0 degrees with respect to the other one. So that means that I'm not changing. We are still gonna have here horizontal polarization. So, and we're gonna have the same amount. So think about when you have any retard there, you change the polarization state, but you don't reduce the intensity. So if the angle, the fast axis of the halfway plane was instead of 0.45, we will not have horizontal, we will have vertically linearly polarized light, but still having 50. But it's important to know where it's gonna be the direction, because then we are passing again to a linear polarizer, but now the angle with respect the vertical, we know that is 30. So we know that the angle with respect to the horizontal is gonna be 60, because that is 90 degrees, right? And they want us to know what is gonna be here, our intensity. So we know that here what we're gonna have is, if this is I0, this is I1, I'm gonna have here the same amount. So we can apply here the Malus law. So we have that the total intensity is gonna be, where I have my input intensity, cosine square of the angle. So that's gonna be the initial one, half of the initial one, cosine square, or 60. So we know that cosine of 60 is 1 over 2. So here we're gonna have it an eighth part of the initial one. So that is kind of like 0.125 I sub 0. So this is gonna be, we are getting almost 13%. Where it's key for this problem is to notice that every time that you have a linear polarizer, sure, there is a drop of the intensity, but when you have a retarder, we don't need to drop the intensity, we just change the polarization state. To finalize the multi-choice questions, let's do some calculation of Stokes parameters. So we have two incoherent. So here the key is when we have incoherent, we need to think about incoherent equal Stokes summation. We need to sum the Stokes parameters. So we have two incoherent lines and they told us the individual Stokes parameters. So we know that the resultant line is gonna have the Stokes parameter is gonna be the summation of them. And if we sum, we're gonna have 2 minus 1, 0, 0, plus 2, 2, 1, 3. So we're gonna have here 4, 1, 1, 3. So this is gonna be the resultant. So obviously we already know that this is gonna be A, but just check it. Let's do the degree of polarization. So this is gonna be S0, S1, S2, and S3. So we're gonna have the square root of S1 squared plus A2 squared plus S3 squared over A sub 0. So here what we're gonna have is 4, 1 plus 1 plus 9, so that's gonna be 11, and it's 0.829. So obviously this is gonna be our correct answer. Something that I want you to notice is there is another way of solving this problem, and it's just looking the degree of polarization. The degree of polarization needs to be defined between 0 and 1. So B, C, and D cannot be possible. So that's the other way that you can do it without solving the math. I hope that helped you to understand polarization optics. Thank you.